So, thank you all for coming to my session that I entitled Performance Mythbusting. Now is the time when I tell you that this is all big hoax and kind of a lie, and then I'm going to do something totally different. No, it'll be vaguely related. Wow.
All right. Now, stop.
Maybe.
Perfect.
Okay.
Stop
Let's start
again.
over.
Right, my boss is gonna
You're on the
watch
camera.
this.
It's fine.
No, I'm starting over.
Yeah. Oh Jesus! Okay. All right. Mike.
Yeah. So, all right. So this is performance mythbusting, but when we talk about performance stuff, a lot of people take very specific bent on it, and that is not mine. I have a very different opinion about what we're going to talk about than perhaps I led everyone to believe in. For that, I should be sorry. So, given that, this is the gist of what's going on. That's not how this works. That's not how any of this works, because pretty much, I'd like to start by saying almost every performance tip that you can read online, as sampled by my various trolling through Medium and screaming at the top of my lungs, is wrong, is useless, and is completely pointless in 2019. My intro. We're going to go on why that might be the case, because we're going to talk a lot more about what modern browsers and modern JavaScript engines are doing, how that stuff works, what's actually happening, the tips and tricks of what's going on behind the scenes, and why it's probably a bad idea to try and outsmart the compiler, and probably a better idea to work with the code and write something that does optimize the parts that you want to. So this is not going to be a big session of tips and tricks. This is not just going to be going through a bunch of things and saying this is slightly bigger, or like the article I read today, which was absolutely outraged because array map was 10 microseconds slower. None of those things are actually what I'm concerned about today. I'm concerned about the big picture. Okay? All right, cool. So the reason that all that matters is because we're going to start here. And this was a slide that is by Google. It's by the V8 team, but we are going to use it in a number of ways because it's not just by the V8 team. I will click the right tab eventually. It's not just about V8. It's about pretty much every modern compiler, and which about basically means every modern JavaScript implementation. The exception of intentionally low-powered device implementations that run on very small browsers and very small footprints, everyone basically follows some version of this, and even they have a version. It just might be slightly different. For the most part, modern JavaScript is not an interpreted language. Modern JavaScript is not even a basic reasoned about language. It's a complicated language, which is a dynamic language, which is optimized through a series of techniques that involve both dynamic language optimization and static analysis of runtime code, which we'll talk through. They all look something like this, though, okay? And then we'll get into the specific version. So you're going to see me talk today, and hear me talk, I suppose, even more so for those of you who aren't looking. But you're going to hear me talk today about this particular implementation in V8 a lot, or the particular parts that we want to, because it's most accessible. It's really easy to download V8 yourself. It's moderately frustrating but possible to get building yourself if you want to really go through and dive through a lot of these things. You'll get to see my really evil version of JS bin that I wrote that takes in JavaScript and spits out assembly. It's great. So we're going to go through all of these sorts of things, but we need to start here. So JavaScript source. When you create JavaScript today, it's parsed. Okay, that's not a surprise. Almost every tool we use in any tool set is a form of parser today. We look at something like ESLint, we look at any of these things. All of these tools are taking JavaScript code and they're parsing it into some form of abstract syntax tree. And that abstract syntax tree exists so that we can describe a language in such a way that we understand what are valid and invalid rules, we understand parts of it, we understand how we can compose and reason about things and aspects of that language. So everything today that's a modern JavaScript implementation is parsed and then it's taken into an abstract syntax tree. Now what happens after this is variable, okay? And it's variable even in a custom browser. Like what Chrome does today is actually quite a bit different than what it did several years ago when I talked about Chrome, because there's a lot of really smart people that are working on it all the time. But the concepts are the same, okay? So conceptually, after we've taken our code and we've broken it down to a bunch of tokens, and we put them together in a syntax tree, we understand things like expressions. We understand this is a function expression. We understand that we're ANDing together two things. We understand that we're adding together two numbers. But it's sort of a tree-like structure at this point. We hand that over to something that, in general, we'll call a baseline compiler, and we'll get into the specific versions for different instances. But everybody has one, whether you're on Safari, whether you're on Chrome, whether you're on Edge before it's Chrome, whatever you might be on, there's different versions of this. But basically, baseline compiler takes those. Now, we can do different things. But already, we're getting into the realm of stuff that invalidates so much of what we talk about. Because who here's worked in a language other than JavaScript, a compiled language? Okay, most of you. Do any of you have the expectation that if you were to open up an executable file, that it would look exactly the same as your source code? Okay, then we should probably stop having the expectation that when we write a lot of JavaScript code and move 2 lines around, that it's going to have a very large impact on what the compiled source looks like as well. This is a compiled language. This is a language where we have a compiler that's applying rules and figuring out what the best way to take that abstract syntax tree, which is already no longer your code, it's an expression of what you meant, and turning it into something that's going to execute. Okay? So we already have something that's been applied in such a way that we are changing the source material into something that is more desirable for execution at this time. Now, the degree to which we do this and how we go about doing this is a matter of very subjective argument. Okay? Chrome in the past has been very aggressive about it, and then they realized that was very problematic on mobile devices, so they backed off on some of it. So things have changed over time. But one way or another, we have some form of baseline compiler, and then, depending on the implementation, depending on what we're working in, we may go right to machine or may go to some form of bytecode. Okay? The difference being, bytecode, i.e. Java, i.e. that's the first stage Java, other things, is something that is then later used by a virtual machine in order to be executed. Machine code is literally code that could, theoretically independent of the original runtime, run on a machine, because it's written in instructions that are native to a processor. So all of these go to one or the other, machine or bytecode at this point. Now, there are other stages that are possible. It's entirely possible that we might come from this baseline compiler, and we might come over here to the optimizing compiler side. And the reason we might do that is that we might see that something could really be optimized. It could be changed. But more often than not, compilers aren't stupid. If you're going to do something exactly once or twice in an application, they're probably not going to waste their considerable effort and your considerable battery going from here to here for something that happens once or twice. So the big reason that we see between here and here generally tends to be things that happen again and again and again and again and again. In fact, in some of the examples you'll see, in order to even get code that would generate in such a way we can look at it, I had to do something thousands and thousands of times, because otherwise the compiler just didn't care, because it was faster to run it right here than it was to spend too much time optimizing it if I wasn't going to do it a lot. Okay? But those are the things we should care about, by the way, because we really shouldn't care about whether we can shave a couple. Okay, taking a step back. In general, we shouldn't care about whether or not we shave a few microseconds off of something here and there. Okay? There's usually better concerns. There are times, and I back this up saying that my background, a lot of my background is embedded programming. Okay? So I know when there are times that you need to shave a microsecond off of something that's important. Most of the time, it isn't here. Most of the time, the articles I read about today about 10 microseconds of saving is not really all that important at the end of the day for the user, okay? So this gets into part of what we're going to talk about a lot. It's this whole idea of us trying to optimize code that, by the way, is going to be optimized with or without us in many cases, but making things more obtuse, making things more difficult, making things less understandable, and trying to outsmart the compiler, all to potentially save a few microseconds and only like an extra 6 months of maintenance, okay? So,
the user has any control? Where does it go from the baseline?
The user, well, the only control that the user would have, the question was, does the user have any control? The only control in general the user would have would be if there's something that they interacted with which caused something to happen more and more, then yes. But in general, the user is making none of these decisions, okay? Now, if you're writing code that's using this pipeline, then you can have all kinds of control. In fact, there's only 240, 250 flags you can pass to D8 that if you'd like to configure it in very specific ways, I wouldn't recommend it. So I did get some of them working. But here, moving from baseline to optimizing is a heuristic, and it's a decision, and it's a decision made with incomplete information. it is always this idea that whether it be your node runtime or it be a browser, that something, whether it be frequency of execution, the number of times that we go through things, something has triggered a heuristic that says this is probably worth optimizing. Okay? The interesting thing about that is that there is an error that you're going to see going back here because sometimes it's wrong. Sometimes it optimizes something with the information it has available, and it turns out it wasn't a good choice for whatever reason, especially in dynamically typed languages. Okay, but optimizing compilers generally go to optimized machine code. So we'll be able to see this today, that depending on what we do, we may get code here, we may get code here. Most likely we're always going to get code across both of these, because some of it is going to be here, and the stuff that made sense to go through and optimize is going to be here. Okay? And we'll see the difference. But going with my original question, which if you can't tell is going to be leading over and over again for the rest of the time, so we might as well get used to it. Hey, if we started out with JavaScript source, that was then parsed, it turned into an abstract syntax tree, and then compiled and then eventually gone through an optimizing compiler, how much do we think that looks like the code we wrote? Okay, so how much does anybody think at the end of the day where they positioned a variable in a function is going to matter a whole lot at the end? But don't worry, there's at least 100,000 pages on Medium devoted to this concept. And again, if I haven't said it already, most of them are wrong. Okay, so actually, that's not fair. I'm being contrite in this way. It is situational. In a given situation, optimizations are worth it. The problem is that situational advice is often applied in a general way where it doesn't necessarily make sense. Okay? All right, so we're going to kind of go through a lot of those fun things. But let's talk first of all about V8. So you see the same boxes, but just throwing in some names, okay? Modern V8 or modern-ish V8, same gist up here. When you see ignition, that's the name of this sort of interpreter that actually runs first. Now, it's ignition. Turbofan is the compiler, okay? Used to be things like crankshaft, they stick with the engine metaphor, but basically the gist is that we start here, which gets us to bytecode. If we decide to kick something over the fence, we go to turbofan. And if we go to turbofan, then we come down into optimized machine code, which may be de-optimized at certain points in time to come back to bytecode if we need to. Okay? We'll talk about the reasons that we do those things. Now, one of the things that's really important to understand, dynamic languages such as JavaScript actually often are perceived as being less performant, but less performant out of necessity. Meaning that people believe because of the fact that we don't have the information from a statically typed language that we can't possibly do the same types of optimizations. The interesting thing is that it may be 100% the opposite. If you think about a statically typed language which has to make optimization decisions while we're writing code, we have a signature of a function. We have to kind of know all the possible things that could be passed to that function now, and then the code could be very solidly written. Okay, but where we have things that are isomorphic or polymorphic, where perhaps we pass in an object that can take several different shapes, well, can we do a good job of optimizing for every possible different way that we get an interface in? Certain languages do, certain languages don't. But we are making a lot of decisions with incomplete information. In fact, imagine a function which in JavaScript is very reasonable, and is reasonable in other languages too, that sometimes operates on a string and sometimes operates on a number. Maybe it's a function that takes objects, but those objects are going to have different shapes. What's interesting about this sort of pipeline is that we don't have to just optimize for the idea that we're going to get an object. We can optimize for the idea that we have only, in our history of running so far, ever seen that we were called with numbers. We can optimize for the fact that we have only seen ourselves being called with objects of a certain shape. But what we can do is that we can optimize not just on the static flow of an application. We can optimize based on the execution of an application when we get to JITting, when we get to just-in-time compiling as opposed to statically compiling up front. So it's this idea of being able to have two pieces of information, and it's more than two, but let's say two pieces of information we can work from. It's what was statically written, but it's what really actually got passed around at runtime that we're able to make really big decisions on. There are always compromises between these things, but it's really interesting because it doesn't necessarily meet the model that everyone else is talking about. And by the way, in the everything is old is new again sort of world of this, if you go read about V8 and you want to, 80% of the things that will reference are small talk, which are going back to the 70s in terms of what you want to read. That's how it works. The things that were pioneered 20 years ago and more are the things that are finally now technically possible in these current platforms, okay? So a few things that are going to matter, and this is why I'm going to reference this, is typing. Typing's really, really important because at the end of the day, I don't mean the kind of typing where I declare something up front. I mean the kind of typing of in, what did you hand me? I'm a function, I'm going to do some work, what did you call me with? That's a type, and I need to know some information about how to work with it in order to do something. So typing is probably one of the biggest pivots on how that optimized machine code is going to look at the end, and when this pathway of de-optimization is going to happen, okay? It's when something's invalid or when we declare something new. Now, let's talk a little bit about what static typing of dynamic things looks like. And I'm not going to get as deep into this as we might otherwise, but it's worthwhile to understand a little bit about what's going on inside of these layers in both traditional languages and in JavaScript in order to understand how something is going to approach the optimization of this code and when it's worthwhile to change something of your own. And there are ways that you can optimize this, and you should. We'll talk about that too. All right, so in general, let's say we have a basic object. In any other language, not any, yes, in any statically typed language, okay, a very statically typed language, once we compile something that's an object, once we compile something, it can even be a structure in C, okay, or a union of structures, but once we compile something, we actually don't really so much care off the beginning of an object what the name of something is, as we generally care where it's located, okay? We know that from the root of any object, if we stored something at 2 bytes from the front, or 10 bytes from the front, or 20 bytes from the front, we can index off the beginning of an object to find something. Anyone who has ever worked with an array hears that arrays are fast because one of the things is that you can index, right? It's very easy to randomly seek into it and know right where to go as opposed to kind of like iterating. Well, with objects that are statically typed in some capacity, one, knowing the root of the object and having, let's call it a map for right now, of knowing what properties were located where in that object's memory can very quickly index into an object in order to find something. And this is this is extremely important because it's part of what makes these things so fast in other languages, is that we don't have to dynamically figure out what X meant if X is a property of an object at runtime. Instead, we know that X was located 4 bytes off the beginning of this object, so we don't always look up X. When we get an object and somebody wants X, we go 4 bytes off of it, we grab the data, we return it to them. That's really important, it's really fast. Those things are quick operations in memory. Alternatively, a lot of dynamic languages work by lookup tables or by hash maps, where every sort of object instead really just has an entry into a hash map that tells us where to find it. And that makes a lot of sense from a certain perspective, because if an object is mutable, I can add properties to it and I can remove properties anytime I want. It's really actually quite hard to figure out where something will exist in that object. And one can say things like, well, maybe I could add them, always successively, but coming back a step, there's nothing stopping me in JavaScript from not adding Y first and then X, or X and then Y. So order can't really be the thing that we think about in terms of how these work. So in most dynamic languages, we keep a map. We keep a map that says, all right, I get this type of object, I get out my legend, bam, I can find the property and go look it up. And it works really well, but it's also not very fast. Okay, it's very hard to do that quickly. And that's part of the reason that oftentimes it can be slow to do member access inside of these languages. But there are multiple ways to handle it. The one that's particularly intriguing in terms of what is pioneered in this is this idea of hidden classes or pieces behind the scenes. So talking about this for a moment. Basically, that map we're talking about is really tied to a type of thing. Meaning, it doesn't have to have a name like it would maybe in another language. But I can say objects that have an X property which are numeric are a type of thing. And so objects that have an X property that are numeric are a type of thing, and I can decide that's my map for that, and I'm going to keep it, but I'm not going to keep it as a lookup table. I'm going to keep it and say that this means for objects that are type X that have a number, X is going to be stored 10 bytes from the beginning of this object. That's where it's at. So what I have now is I've kind of got a hybridization of the idea that in a statically typed language, I would have known where X was going to be. And in a dynamic one, I have to look it up, but the cool part is I have the flexibility of changing it all the time. So what's actually happening in here is that one of the first times we see an object with X, we go, oh, that's interesting. That's an object and it has an X property, so I'm going to take the opportunity right now to basically build up what's really kind of a class, like you would think about in object-oriented language. Behind the scenes, it says, got it, here's my static version of what that sort of object looks like. Now that's really cool and it makes it super fast. Of course, it gets slightly tricky because then I come along and I add a Y property. Okay? And there are some objects in the system now that have X properties, and now there are some objects that I took their X properties and I added another property which is called Y. So what happens is that we actually have this sort of list-ish sort of concept where each of the properties can be added, and every time we observe a new object with the same properties, we basically make a new class. It's not exactly, but you can loosely think of it like it's building up inheritance behind the scenes, where it's pretty much saying, okay, I understand that properties with a Y, objects with a property with a Y, kind of-ish inherit from properties with an X, but we can think about that even though it's not 100% right for a mental model here, in terms of what we can do. So one of the interesting parts is that once we actually have observed objects with these different properties with the same types, we can start building quite a bit of information about what the types of objects we're going to be routinely dealing with in the system are. And they keep getting faster as we're building this information because we know how to access them very, very quickly. Okay? There's another reason, by the way, and you'll hear this a lot, but when people do performance profiling, a lot of it is looked at as in, oh, okay, well, I know I can't just run it once, or I can't just run it twice. That I know there's some startup time, but people don't always necessarily understand that, especially in modern languages. It's not once or twice. It might be that I access something a couple hundred times and then the compiler says, hey, it's worthwhile now to do some work to it. It's worthwhile to actually go off and do something. So it's trying to optimize on decisions for the long term, not for decisions on the short term. Okay? Now, it's interesting because behind the scenes, technically if we have an object that has just a Y property, we have to have a different class for it. And then if they add an X property, then we actually get to transition to this and go, oh wait, now we know what that is, because we've seen objects with X and Y properties before, and we can make that work. So there's a lot of complex mapping, not math, that goes into keeping these behind the scenes. So there are real actual optimizations that you can show by trying to make sure that you always pass around objects that look the same. I don't know that it's worth it, but the idea is like that's actually where the real low-level stuff actually matters, because it's an implementation detail in terms of how this thing comes together. Does that make sense? Okay, so they call them, what was that?
Say anything.
Always something, Joe. Always something.
Joe's too embarrassed to say no, he's no idea what we're talking about.
It's okay, Joe. It's okay.
I'm not embarrassed.
All right, so to that end, what we can think about this is, depending on the literature you see, you'll often see these called hidden classes, and some of this is older stuff and mixed with newer stuff, but the idea behind it is that we're sort of overlaying a structure onto dynamic objects to make them more static, but we infer their staticness at runtime from dynamic information. Okay? So once they get to a certain point, we can consider them static, even if truly they're dynamic. That's really powerful. It makes things way, way, way faster as we go along. Okay. Here's one other part we're going to talk about really quickly. Execution. Those of you who left, because I memorized Christian's definition of this before I left. Christian, who works with me, has got a very precise way of defining things, and I appreciate it and respect it. He's a little better at that than I am, to be completely honest. But execution is king in JavaScript. In fact, execution is the only thing. The way that you pretty much create a function, especially if it's more clear in sort of ES6, but we create a function and we might assign it to a constant or to a variable. We do these sorts of things that everything involves what we execute. When we load up a module, which is its own sort of scoping and concept, when we load it up and we run the code for the very first time is when we understand what the definitions of that are. There's no understanding of things in JavaScript until execution occurs, okay? It's all about execution. So the thing is that if we have a whole bunch of different things out there in the world that, for instance, get executed, but they don't have any viable side effect, meaning they get executed, but they don't log out a value, they don't return a value, they don't write a value to disk, they don't shoot off fireworks with the value, there's no observable side effect, it doesn't really matter so much if they're there, okay? Because from an execution point of view, they're not. It doesn't matter, there's no way to know that they did or didn't run. And if there's no way to know they did or didn't run, they might as well not have run. okay? But also, it means that when we have lots and lots and lots and lots and lots and lots of functions, what do you think something like an optimizing compiler does with a whole bunch of functions that you never call?
Ignores them.
It tosses them away, doesn't do a damn thing with them, doesn't care at all. All those would be valid answers. So we're going to get into this a little bit, but I'm trying to put everybody in the mindset when we start going into some of this, that the way in which we're talking about this and what this is going to do has to be wholly different, because we have to think a little bit about what the compiler is likely to do with the things we're trying to do. And we can go look, and we will. But when we get to some of these performance tips, and when we get to some of them that maybe sound like really good ideas up front, if we put them in the lens of understanding that all this code is parsed, all this code is compiled, potentially optimized and put out, we have to really decide how many of those things are really practical when we're trying to manipulate it from the source code side. I like to think about it as that we're trying to move stuff with the small end of the lever, okay? We don't have the majority of how this code gets written. If anything, at this point, your JavaScript is a strong suggestion to the environment on what you would like done. And based on that strong suggestion, it does what it thinks is appropriate. We have to remember we're making strong suggestions. Doesn't mean we can't do things to screw that up. But on the whole, we spend a lot of time on things that don't matter that much. All right, so let's talk through some of these. Sir?
Or how objects are looked up? Or is something similar going on with arrays then too?
They're something very similar. So arrays are, so the question was, is something similar going on with objects, with arrays to objects? Arrays are able to be more contiguous in terms of blocks of memory, okay? Because complicated values aren't really stored in an array position. It's a reference that's stored in the array position to somewhere else, okay? So arrays can be contiguous blocks of memory, and there's a certain overhead in decision making on how big to grow, to make those, when you should grow them, when you can do other things. But they already have the ability and they already have the benefit of being ordered. So we can generally jump into locations to begin with. So I would say it's kind of almost the other way. It's like objects are becoming more array-like if you think about it in this way. There are some different pieces when we get in different implementations do different things with sparse arrays when we get to it, which would be arrays not with empty values or not with a value that's empty, but rather with values that are missing, like as in there is no index for. So different people optimize those in different ways, and sometimes that can be slower and faster. But I would say it's kind of the other way. It's like arrays were actually almost our way of going, and we've kind of gotten there. Okay? All right, my N+1 tips, which we will get to and we will go through and we will have all kinds of fun with. These are drawn from various articles I've encountered while searching very easily, because really one just needs to type in performance trips JavaScript and you can read for days. And most of them reference each other, and see the aforementioned, most of them are wrong, at least in all the useful contexts. All right, so number 2 should be in a different place, but that's okay. Number 2 should be right down near number 5. I like to avoid local variables along with use global variables and avoid global variables. I like to keep those all three together. So the, and these were all, just to clarify, I didn't go combing anybody's blog. These were all really top-rated articles on performance. I did change the names so that most of these shouldn't be directly Googleable to make fun of the author. And I didn't include any of the author's original names. All right, but I want to talk about a couple of these first ones. Before we even go much further, let's talk about number 1. One of the biggest performance tricks. We should remove all the unused JavaScript in our project. All right. Tell me where that will and won't matter.
You're not using a bundler.
That would be step 1, right? If you're not using a bundler, that would be true. Where else?
When it comes to doing the review of your application from the front end.
That's politics.
Yeah, you know what? I was going to say something
Yeah.
similar. It's, I mean, part of the developer experience when you have a whole bunch of dead code. So it's
Sure.
not an optimization for a compiler. It's
You know what?
an
I will
optimization
accept that.
for-
So the point being,
Whoa, wait, he says it is fine?
yeah. Yeah. So,
That speaker, man.
yeah. So the points raised from the peanut gallery were that a client might be reviewing our code, which is valid and actually related to Joe's point of there's mental just clutter in terms of looking at a bunch of code with unused JavaScript. I will agree to both, and anyone who's worked with me will know I agree to both. I'm known to just delete entirely useful pieces of code before committing it right to Git. But but nonetheless, I agree with both of those things. And If you're using a bundler, certainly we already have bundlers that are doing some of this work for us. The one place that I'll say removing unused JavaScript outside of those pieces that can still have an impact is if we are delivering something over the wire and we're sending tons and tons and tons of JavaScript that we don't need to. We're sending bytes we don't need to. A low-powered device or a device that has to hit the antenna, uses a lot of battery. Okay, I'll give that one as a possible optimization on that front. And now let's talk about it in terms of actual runtime performance. It is definitely true that it does take a handful of microseconds for the compiler to notice that there's a function there and to also notice you didn't use it. Okay? Because if we think about it in reverse, it's not that we have to scour the code to find out if somebody used it. Let's look at my aforementioned example of sort of these ideas of execution. If nobody executes it, I don't care that it's there. I never do anything with it. I don't compile it. I don't try to do anything with it. So does that really actually help us? To be clear, the answer is no. But it doesn't, right? And we can see this pretty quickly and pretty easily if we actually start looking through what happens and if we want to kind of get into these things. And we do, because you're here and you came despite any warnings you got about me previously. All right, so we're going to look at my evilish version of what I was calling earlier, although I tweaked it back a little bit, but I was making a JS binish kind of concept where you wrote code and it gave you assembly, which I thought was kind of fun. As we went along and did some comparing and contrasting. We're going to just keep me focused on what time it is because I'm just going to keep talking until you tell me to pause, all right?
You have about 10 minutes
Thank you, sir.
before the first break.
You are a gentleman, a scholar, and a man wearing blue. All right, so let's look at these really important functions here, okay? So we have functions 1 through 10, which I have intentionally named not used 1 through 10. I struggled a lot with the naming, but I eventually settled on that. And then I have number 12 there. What was that? You know, I've already zoomed it in.
Wherever it's comfortable. You got people way in the back.
I know, you're right. That's why I sighed and didn't argue with you and just did it.
It doesn't care about users.
So, however, I may not be able to fix all the next ones, but because I don't know how. And I didn't investigate. But maybe I could do that during the break. Good point, Joe.
You're welcome.
All right, so I have not used 1 through 10. Those functions aren't used. And then I have a function called please give me x, which takes something that has an x and returns it to me. And I use one of them, please give me x, and I pass it an object. Okay? So let's make sure that my compiler little thing is running. It is in the background here. And we'll get into this a little bit. We're going to do some comparative differentiation stuff later. But let's just go look at the output first as a starting point. All right, so here's a little easy to read assembly for you. Actually, technically, this is bytecode. All right, we'll get into the assembly part in a little bit. So this is the easier stuff. We don't have to go through what every instruction does right now. It doesn't matter. But I wanted to show you a couple things. And we'll have a little bit of fun with this as we go along. But this is our first stage. When we go back for just a moment here and we talk about these, we're talking about this stage, the machine or bytecode stage right now. So this is what it looks like when we actually run E8 or V8, depending on what you're running, in this mode. Now, you can do some of these same things with Node. Node will actually let you pass a number of flags in to see the same sort of information. There's a little bit more clutter, though, depending on how you do it in Node, because Node has its own environmental things going on. Whereas if you can imagine, if you're just compiling the V8 engine and just invoking it directly with a chunk of JavaScript, you can do whatever you want to do. And it really does work that way. Actually, let me go here real quick. Easy for me to say. Let's go to V8. I think it's in out and debug, or x64 debug. All right, I will figure that out. Hold on. This is not something I do very often.
Font.
That's a good idea as a starting point. Let's go to 36. There we go. All right. So if one goes through and follows the steps that Google provides, some of which are accurate, you can build D8 from source. Okay? And so if you build D8 from source, you can build it in two modes. You can build it in debug mode, or you can build it in a release mode. And if you build it in debug mode, you can see a lot of cool stuff and things that you may not have seen before. They're both very useful, though. And the interesting thing is that you can go in and basically just do simple things, which aren't surprising. You can do this in Node 2, where you can just execute code. But you can also pass it functions, and when you're doing that, you can also ask it to do a lot more. Like you can say, do me a favor and print the bytecode. And it's like, I'll be glad to do that for you. And when you say 3 plus 3, you find out exactly what's going on inside of it.
That's awesome.
All right, so what I have here is a tiny little script that watches a couple directories and automatically kicks everything off to D8 so that I don't have to keep running it over and over again. And then it diffs the last version and the current version so that we can do some comparative stuff as we tweak things along. Okay? That's my evil JS finish sort of thing. So to that end, what we can actually look at is we can look at this code and then we can look at the output of this code. So as a starting point, we don't have a lot going on here. We just have a bunch of unused functions. And it might be hard at first to parse this, but we're not going to care about all of the pieces. We're going to pick some random little things out of here when we look at it. So when we start going through here, what we are going to notice is some really interesting pieces. When it comes down here, we're going to see generated bytecode, and it's kind of fun because this is going to tell us, we have a little mix of questions on. We generated bytecode for exactly 2 functions. One was kind of our initial scope, our whole function that we're in when I run it this way, okay? And then the other one was for please give me X. What didn't I generate any code for?
The unused ones.
There ain't nothing there. They don't exist, okay? And so that whole idea that perhaps I should reduce the size of what's going on by going through and reducing this is pretty fictitious in terms of what's actually happening in a JavaScript layer. Now, there are places that you can see references to them, and that's because this is an execution-based dynamic language. So what it really does in some cases is that it goes through and it says, well, let me kind of put a hook, for lack of a better term. I'm going to put a little function or a little piece of code here that if somebody calls this code in a way that I wasn't expecting, because JavaScript's pretty crazy, right? I could take the window, I could dive down through an object, I could pass it the name of a string, and I could try to invoke a function that I know is supposed to be there. Okay? If I do that, it has a little hook that says, ah, crap. Somebody really was using this. And at that moment, it goes off and compiles it. And it uses it and it gives it to you. But until the moment that you execute it, it ain't there. And in fact, if we were to go back and if we were to say, we don't want to use that at all, and we were to come back here to our code, we'd actually find out that, in a moment, let me do the diff on this one, we would find out that that stuff's going to go away here too. Sorry, I will increase the font size during the break for this one. Oh, stop being a pain in the ass. 1 second. My little watch window has been acting up a little bit. Oh no, it's just saying type better dummy.
3 minutes.
So type better dummy is my log statement when I type bad JavaScript. And in this case, logging out A when one did not define A does in fact not pass the please type better dummy test. All right, so let's go look, demo1.bytes, and there we go. There is our demo1.bytes. Does everybody like it?
Beautiful.
Everything's execution, folks. If I don't execute anything, what's it got to compile for me? Doesn't care that there's a bunch of functions right now. Literally, there's no code in the project that runs any of them. There's no observable side effect. You can't tell for sure that it didn't compile them all. Maybe it did exactly its job and got them all ready for you. You don't know. They aren't there. Maybe they are. Very Heisenberg of it. So either way, it isn't there. We don't know. We can't have an observable side effect. So that's life. That's what demo1.bytes looks like right now. Make sense? Okay, so keeping this in mind for everything else we're going to do, we're going to start applying all these sorts of things when we look at everything that's going on. Because we have to think, are we, and it really comes down to it, this is really going to be the decision, and it's sometimes an ego assuaging thing we have to work through. Am I smarter than the compiler? Okay, because that's the real question. All right, I am supposed to give everyone a bio break while the camera changes.
The camera needs bio break.
The camera also needs a bio break, so take a bio break and then come back in a few minutes, hopefully, and we'll continue on. If you all leave, I understand, and I'll still talk to Joe and make him stay. All right, so when we last left our heroes, we were looking at the fact that we got an excellent compare of no code at all. In the meantime, I spent a lot of time trying to figure out how to increase the font size on my comparison and managed to figure out how to change it in TreeView, but nothing at all relevant when you actually look at the comparison. So we're going to have to do this a different way, and that'll be fun. No, it won't, but we'll figure it out, and that'll be great. So we're going to go ahead and kind of go through that. But I wanted to keep talking about some of these things in terms of what we see. So right now, I actually talked a little bit about the fact that we now have nothing. And we have nothing because, well, we executed nothing. And so, well, I mean, it's not true. We did execute something, because everything's execution in JavaScript. But at the end of the day, we didn't execute any of these things that we declared. Hence, we didn't have anything that we needed to create. Hence, we don't really have anything our program needs to do. So it all changes, right? But that's the one tier, right? So that's the first tier. Like, do I actually care enough to do something? But that's actually kind of interesting, because all we've seen so far is over here in this little bit of compiler. And in fact, even when I put this in, if you noticed, and you'll be forgiven if you didn't, but if you noticed, there wasn't a whole lot that was other than bytecode, and it's a little hard to see that at first, but let's go ahead and look. So when we go in here and we look at our, and it's a 4, that is true. So if we go through and look at our bytecode that was actually generated from some of these things, what we'll see, what are you doing? Always something, I'll tell you. All right, we'll figure that out in a second. But what we saw is that the bytecode itself, or what we will see rather, is that we have a very small amount of bytecode, but it's all bytecode. There was nothing of particular value that was not bytecode-like in terms of what we did. Now, we can start messing around with how we actually build some of these things in different ways. What is it? Okay, cool. It's fine. Everything's fine. It'll all be good. So we are messing around with what we have in bytecode, but we haven't actually got to the point of seeing anything of value in terms of what it might look like if we wanted to print more code or do anything else. So we haven't gotten to this stage of the compiler. So for fun, before we actually get to that point or talk more about the next sort of steps, let's actually have a little bit more fun with what this looks like. So this ought to be enough to convince the compiler that this is a reasonably important thing. All right, so we'll call that function a lot. We're going to pass it some different values. We're going to do some different things. And once we go through and do a whole bunch of different work like that, we'll take that as an example of something that could be useful to the compiler to potentially optimize for us. Something that would be good. Now, with just a little bit of luck, well, command failed, dummy. That would be me. Let's see what I did wrong.
Have a function called gimme x.
Yes.
There is.
One called please give me x. I was being polite. All right. Fine. I wasn't polite enough, apparently. All right, but now it's game. So that's cool. I got that going for me, which is nice. All right, so we actually have a whole bunch of these functions, which we're seeing now in the way I have it set up. This is our raw source, okay? So this isn't compiled code. It's going to iterate some raw source to us. And the reason that this is going to start looking a little different is we got a cool new section. We got something new we can play with now. And that section that we can do, and by the way, one of the reasons that we'll see this go back and forth a little bit is that the flags in V8 are a little bit crazy. That's the term for it. If you print the optimized code, it doesn't necessarily print the bytecode anymore, which makes sense because it might have gone away. And if you print the bytecode, it doesn't necessarily print the optimized code. But if you print both of them, then they're intermixed and you actually have duplicate code because they're not both there. So we're going to have to play with options a little bit as we go back and forth to not overwhelm everything about what we're looking at. What we have now is something kind of cool. We went away from having bytecode, and we see this first thing here that says turbofan compiler, and we see that this is an optimized function. And so what we did just now is we changed from having something that was previously, and let's see if it's still in here. Nope, that's all right. What was previously just a chunk of code that was optimized at a bytecode level to something that's now it's actually showing us what the actual optimized code is, okay? And it's pretty neat because when we look at it and when we look at these things, we're no longer in the realm of bytecode. We're in the realm of actual x64 instructions, okay? We're looking at something that was done this way, which means if I was on a different type of machine, I would get different instructions at this point because it's compiling from my machine. So that happened because a decision was made, and the decision was made internal to this, not because of the very first time, not because I called it here, or that it saw that it was going to call it a bunch. It's because it was called. As it started being called more, it noticed that it was being called. And as such, when it noticed it was being called, it said, this is a candidate for optimization. And it went forth and it optimized it, okay? And that's really important and really interesting in terms of what it's doing. Because when we go through, some of the reasons it could optimize it are those things that we talked about before. And this part right here is going to be really, really important next. Because one of the reasons it was able to optimize this for us is because it was able to understand that it has a certain shape. In other words, it knows at this point that this is the type of function, please give me x here, okay, was the type of function which it was only really going to care about ever going after an x. If we go through and look, we could actually find down here that we'll see some bytecode offsets for some certain things that we've actually created. But if we follow this back through, and we won't do it at the moment, but if we follow this back through, we'll actually see up here the address for the offset of x, okay? It optimized this code because it knew that it was going to get lots and lots of things that were given an x. So it didn't write a generic function that could take any type of object in the world and go get x out of it. That's how we think about it in JavaScript, but that's not what it did. It wrote an extraordinarily specialized version of a function that understands how to get objects that look like this. And it was okay if they looked like this, because that's kind of a descendant, okay? If they have an x and a y. It was really, really important that they at least look like this, okay?
Sorry, like in a real browser, will it actually compile it to the machine code?
Sure will. You can actually turn on the flag. The question was if, a regular browser will it compile the machine code? Yeah. You can actually turn on these flags in Chrome if you have it and watch what's happening. So yeah, it's there.
So JavaScript is actually executed like directly on the machine. It's not in a sandbox.
So yes, it is executed on the machine. The memory references, and there are some controls in place, because that's the first time I heard that too. I was scary as hell to think that any JavaScript on this page was actually executing on my machine. But yes, at the end of the day, removing all of the stuff around it, yes, it is executing as machine code, okay? And it is, in my case, x64 machine code, okay? Now, we've written something that takes this, and it knows how to take this. So it's written a function for us that understands how to do that. That's it, though, okay? This is not a generic function that knows how to return anything. It's not a generic function that knows how to even return for other objects. If I pass it a point object, which happens to have an x property, this same code I just compiled will not apply to that, okay? Because that's not what it wrote. It's just like a statically compiled language at this point, that it wrote a function that is super determined to do that exact one thing for you in a really great way. But it also has all these little bailouts, okay? And if we go through and look through this, what basically we can read is that it's going to go through and do some checking and some testing. And then it's going to have these jump points, okay? And these jump points are kind of interesting in terms of where we go down here, because we'll see these things that say, eager de-optimization bailout, okay? And what that actually means is, I went ahead and I optimized this code for this specific object because in the lifetime of your application, the only thing you've ever given me is this one. So I wrote the code for what I believe to be all the cases in the universe. This is what it is. The universe is only composed of times when you call me with an X property. Game on. However, what happens when you give me something that wasn't that same thing? And again, I do not mean any object with an X property. I mean this object, one that came from this same hidden class. And what it does is it bails out. It catches that fact and it jumps down to here. And it says, I need to bail out and de-optimize. Okay? So if we look at this pathway, and this seems small, but it's pretty big, right? I have a lot of empathy for this machine. And here we are. We're in this perfect world where we're running and everything's been great, and the world is simply full of these really homogeneous objects. They all have an X property, and there is nothing else in the whole world. Everything's happy. We get up in the morning, we know exactly what to expect. Everything's great. And then suddenly someone gives us something that doesn't look the same. Holy crap, the universe is broken. Right here, what we do is we say, yeah. We jump over and we take that and we run back to the bytecode and we say, what the hell do they want to do? And we do it from the bytecode because the bytecode's safe. May not be fast, but it was a safe, literal interpretation, not exactly literal, but literal-ish interpretation of what happened. And we can run over here and we can do things for a while. And then if we do them for a while there, and it turns out that we now see a universe where sometimes we get a lot of these, and sometimes we get a lot of these, we can come back through, and we can rewrite this one to now be a function that understands how to do this and this. Or, what really actually happens is we can write one specialized function that deals with all the x's, and one specialized function that deals with all the y's. And we'll go ahead and we'll let that happen in the universe. But basically, anytime we get to compilation, we're actually optimizing to the cases we have seen at that moment, and very, 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 very tightly. So this sort of, you can hear it in lots of different ways. It's not literally true in JavaScript, but this sort of duck typing-esque idea. Everyone familiar with duck typing? All right, for those of you who are not, if it walks like a duck and it quacks like a duck, let's call it a duck. Okay? So if it has an x property, good enough. We'll call it isomorphically x. It's got an x property, we're gonna take it, we're good to go, game on. But that's not really what's actually happening behind the scenes. We can pass it something with an x property. We expect it to figure out how to deal with that, and it will. But it's not going to do it with the same optimized machine code, because that's not what that code does. Okay? Making sense? And so if we want to give the virtual machine a heart attack, all we actually have to do that is say, please give me x, please give me x, please give me x. And then right down here, if we want to, we can just do something different. 5. That would be really mean, because it doesn't have an x property, and I don't really want to do that. So let's do, I think I said, we'll do one that has a z5 and an x2, okay? Looks different than all of the other ones that we've actually talked about so far. And when we do that, and we go through, we're actually going to see a very different set of optimizations and bailouts. It's freaking out because the world is now different. There's a whole bunch of different things it needs now to do in order to worry about the things that could happen, because you have freaked it out. The world is no longer the same. The world is no longer a safe place that just has x's.
Is this why Chrome takes like 17 gig of RAM?
The question from the peanut gallery is, he'd like me to address the concept of computer science, that things can either be fast or take a lot of memory, but that performance optimization and memory optimization are usually inverses of each other.
Yes, that's exactly what I said.
Yes, this is why. But, so Chrome does take a lot of memory. It takes a lot less than it used to, partially because of this. It used to, so let's actually talk about that for a second.
Oh, by the way, you have like 45 minutes.
Again, we can get to you next month. All right.
Lightning talks. Yeah.
Actually, side note, I don't want to take all 45 minutes to explain this, but one time I did a lightning talk and it was great. It was in Sydney. But what happened is I had an hour-and-a-half talk and they accidentally scheduled me for a 20-minute session. So I just got it all in.
So you hate us.
I called my presentation dense and hot. All right, so we get over here, and we've kind of gone about the world. We've created this. Oh, sorry, no, going back. These new pieces. Thank you, memory. It used to be the fact that pretty early on, Chrome would almost immediately say, you know what, I should go off and JIT this stuff because someone might. If they called it, they might need it. I'm going to go ahead and do this, and I'll get it all ready for them, and it'll be super fast. But it turned out that was very memory intensive and very processor intensive. And while it was just fine on your PC, on a mobile phone, it was very, very problematic. So instead, they put a lot of effort into Ignition. And Ignition basically now raises the threshold pretty significantly as to when it actually decides it needs to do this compiler step, which is why I'm having to do so many big loops to get it to kick in. Okay? Because it will pretty much stick down here in this heuristic for a while and say, you know what, I'm probably fast enough until it really knows it needs to go to the next level. And even so, there's some other cool things too, like the output of this can actually be directly optimized by this and some other cool stuff. But at the end of the day, it does actually take quite a bit less than it used to. And they keep driving it down, so this new tool chain is pretty neat in that regard. Okay, so going back to my slide for a moment, I think we could probably be okay with number 1 not being the case, okay? We'll talk about number 2-ish, but number 3 is more interesting to me, and since I talk a lot and I've been told I only have minutes, we might as well go ahead and take care of that. So, I grouped all of these together for a very obvious reason. Here are some of the wonderful tips that I heard. Again, let's keep in mind what we know so far. You should put any variables and calculations to function calls that are going to happen more than once, make sure you put them in a variable and right away get them there. Do it once, because we don't want to have to tax anything. Function inlining. If you have a function that was going to do a bunch of stuff, and it was very small, maybe we should just take that and put it right in line instead of actually calling the function, right? So don't declare a function, just put that code right in line. Do it that way. You should take common expressions and have results, combine them. We should never, whatever we do, don't call a function that adds two things. Use the plus operator because, obviously that's going to be much, much faster. If we have mathematical formulas that are complicated, we should definitely simplify them. That it doesn't at all seem like something a computer could do. So we want to do those. Definitely take the time to do those and introduce any errors if possible. And then, if we have objects that are very obvious that we're in a loop or something, and this one, caching's a tricky thing, and so sometimes it's important, but they're talking about it here is well, I'm in a loop, and you're in a loop, and you're doing something, you should definitely cache stuff. Okay, so let's talk about all of those at once. So, we're going to jump right over to this one for a second. All right, so first of all, let's look at some of what's actually going to happen. And maybe we'll bounce through this for a second. I don't remember which one I want to do anymore. That doesn't matter. We'll actually go up and we'll do that one, and we'll tweak it a little bit. All right, so we're going to take our add function up here, okay? And we are going to say that instead of adding that plus operator, I am going to commit a terrible, terrible sin, and I'm going to call a function instead to add those things. How dare I? And in doing so, clearly, there is no chance this thing's ever going to run. Modern browsers will not be able to handle it. Mobile phones will explode. This is the actual root cause of all the lithium battery problems. It's right here. I called that function. All right, so there's nothing that can be done now. It's irredeemable. But fortunately, Chrome is smart. So maybe there's something that it could have done when I called this add function right in here. And it's really kind of interesting because, again, Turbofan kicked in and said, OK, I got this for you. I'm going to go ahead and optimize you because you're dumb. And it went ahead and took care of that for me. And the really interesting thing that I find is this. Hey, we noticed that you were calling this add function a whole lot inside of this for loop. So I just went ahead and inlined it wherever you were at. And I went ahead and just put that in line because there was no use making a function call out of that. I got you covered. We're good. And by the way, if we were going to make a mathematical function, it's probably going to do kind of the same thing. And for the most part, if I do other stuff we'll just take guesses on some of these. These are my favorite part when we do this. This is one of my other ones that I saw. You never want to do this. Whatever you do, this is just a terrible idea, right? Because this extra variable here, we are going to kill performance now. If we go ahead and say that we declared that extra local variable, right? Does anybody at this point believe that that variable is even going to make it into the final code? There's no part of it that's going to make it into final code. There was an entire article, which I nearly publicly shamed because it was about this idea, and everyone in the office is laughing because they actually heard me going on about this several times, not just once. But it was specifically about the idea that whatever you do, you don't want to use local variables in JavaScript. You just don't want to put variables in a function because, when you think of all the time it takes to create that variable, every single time you're going to do it, and then you're using it, and you just have to throw it away at the beginning of the next loop. And it's maddening because it's not true in any language, let alone this one. But it's not how it works, right? That's not how any of this works. This is the idea that we are expressing something. And this became an abstract syntax tree, and that abstract syntax tree basically explained to it that the intent was that I was declaring something that I was going to add together. By the time it got through that compiler, none of that existed in that way. There's no local variable. It doesn't work that way. Even in terms of the bytecode, even if we never optimized it, that thing, the bytecode machine that runs in Chrome, for those of you who know the term, it's more of a register machine than a stack machine. But this thing became, basically was put into a register, the math happened in a register, we were done. There was no local variable from its concern. That's for us to be able to read. And I would strongly encourage you not to abandon things like variables that are local that make things more readable for the idea that somehow we're going to get a performance gain on something that is never going to matter. Ever, 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 ever matter. Okay? Good. All right. So, in general.
So how it should be done?
Any way you want. because it doesn't care.
Oh, I can do that. Can you use jQuery, please?
Yes. All right. I apologize. You are right. There's always a way to be dumber than somebody else. But sometimes you have to work at it. Some people it comes naturally. You are. So all right. So the gist, though, is that in here it doesn't matter because we're expressing an intent. We have to stop thinking about this code being literal translations. We are expressing an intent, and our intent here was that we locally wanted to increment sum by the result of adding sum. And actually, my code's wrong at the moment because I just did a plus thing. But that aside, right? The gist of it is that one way or another, I have, in one way or the other, this local variable, this concept of things, is our explanation to the compiler or to the machine what we want it to do. We don't need to take it as literal code. It's our explanation of what we want to do. Okay? Does that make sense? Now, the same thing is true, by the way, of any sorts of scoping and other execution pieces. It's not that there aren't some performance benefits in some narrow cases. There always are. But in the average cases, these aren't the things that you should be worried about. So, see that sum variable on line 6? There was a whole post about what an awful idea that was. Because the best thing you should do is put sum at the global scope, because then you're just incrementing this one thing. We don't have to waste any time returning it. And then there was an equally awesome article that was like, whatever you do, don't put this thing in the global scope. Because if you put this thing at the global scope, you're just reaching up through this scope to try to get to everything. And how are you going to do that? Because every single time you go to access that, it's got to start at the beginning. It's the dumbest thing ever. It walks up the flight of stairs, figures out where the variable is, like, there it is, sets it, walks right back down, then it's in operation, walks back up the stairs, goes and does it again. It's all homunculus in my mind. Little things working inside this at all the time. But that's not how this works. This is not how it works. So even if we have a local variable on line 6, or if we made it global, okay? For the most part, we're going to take some time in different ways to find out where that variable, or the data associated with that variable is located. And once we do, we aren't going to do it in every loop. We're not going to do it again and again and again and again. We're going to know where it was because that's what our job is to keep track of those things. Computers are awfully good at storing numbers. So once we find out where it's at, we're going to store it. And that's what we're going to use. Now, that said, there are differences. There are optimizations that can actually be done by having line 6 inside that function, right? Because with line 6 being the sum inside that function, and it not being on the global scope, there's zero chance anybody else can touch it, right? There's no chance anybody else can do anything, and that does actually mean that Chrome can be more aggressive, or VA can be more aggressive at what it can optimize, because it doesn't really matter if that variable ever exists. It has a lot of ideas on how it could rewrite this function with no pretense to what it needs to do because that variable is now local. When we put things on the global scope, and this is the interesting part, it's much more about who else can touch it and where we have to be careful of how else somebody might be referencing it. Because if someone else might reference it, I might have to leave it around. I might have to have something there. I might at least have to have a reference. But if it's inside a closure that no one else can get to, I can be a lot more firm with it. Jalen?
So when you said that,
First time caller, long time listener,
yeah.
got it.
So when you said it will inline the add after some time, does that also remove it then from?
Yeah, great question. Okay, so in this case, the question was that since add was here and we showed that it was inlined in the code, does it also remove it? And the answer is yes-ish, okay? So the add function is not compiled on the global scope at all. However, there's still a hook there in case there was some other way, assuming that this module is exported or something in such a way that add could exist. In case there was some other way for somebody to call it, there can still be hooks in the case where those things were exported in some capacity, whether because they're on a global scope or a module scope or whatever the case is. But they won't literally be there in any compiled form. So that function is effectively gone in this case. Okay? And just get one. All right, cool. Joseph?
So your local variable versus global variable section there, it sounds like you kind of reaffirmed that global variables are a bad idea.
Oh, so here's the thing. I have lots of opinion about global variables.
Okay. But I mean, you
Lots.
said it technically makes it harder on the compiler.
Well,
Or could.
Okay, so the question is about whether or not it actually makes it harder on the compiler or the error. And there's a difference between harder on the compiler and slower, right? So if the topic is it really slower, the answer is negligible to not at all, okay? Unless perhaps you construct something where it's a million layers deep and it really has to go searching the first time. But negligible to not at all. Is the question, are there other things the compiler could potentially do to optimize differently if that wasn't global? And the answer is yes, there's a ton of things we could do. So I think it's a very good practice, but if we're strictly talking about and boiling it down to, does the variable indicated here or in the global space make a whole bunch of difference in how fast that function runs? The answer is not really. Okay? So I want to tease apart those two things, because I don't know if you've met me, but I have some opinions on this. So, yeah, it could be. So, and I didn't put the money in the jar yet, but one of you had to be thinking that, because we have a for loop jar in the office. And if you write a for loop without proper cause, you have to put $1 in the jar. I did this for simplicity's sake, but I owe several dollars in the for loop jar. All right, so somebody had to be thinking it. All right, so within this, right, we have a function that was being called. I intentionally actually, by the way, put this in here and calling F1 because in the closure scope then we can actually see that function being created. We can see that there is an F1, it's kind of its own unique thing, or at least be able to trace the code a little bit more. Also, and I think everyone's noticed, but what I'm doing up here is creating a kind of long array. And I'm creating a kind of long array because of the fact that it gives me an opportunity to force the compiler to actually go do something that it otherwise may not have done, and making sure that that thing's going to run enough that it actually cares. Okay, so let's talk for a moment just more about local versus global in terms of things, okay? And there's really two different concepts here. Everything is ultimately execution in terms of things in discovery in JavaScript, but there's really two related concepts. One is our scoping, right? That is the information that we get from where we are defined, right? So when we're defined, or when we're created, that's our closure scope, that's where we are, we get some information from that. We also get information about the execution, or the execution context, which specifically, here's the Christian one, ready? That from which we are executed implicitly or explicitly. Is the execution context. Very accurate, very accurate. But the idea is that we have information about both in JavaScript. People are most familiar with this with function binding, right? In function binding and old school functions, we can change the this pointer. What are we really doing? We're kind of tweaking that context, okay? We're basically prescribing a context in which we're going to be called. All of those things matter because it has to figure out where to resolve it. But I guess the big difference I want you to think about is that it's a matter of resolution. So the overhead that one gets in using something in different scopes and up and down the chain is in finding this instance of something, not necessarily in every iterative version of executing. And that's mostly true. There's little things here and there that are going to be on that, and also it's going to make a difference whether it's compiled or not. Which, going back, side note, if we run one of these things 100 times, we may very well, one of these things I'm saying may very well be wrong for 100 times of execution. Because if you execute it 100 times, it may not be that anyone decides to optimize it. But what I'm talking about is that if you run it 100 times, it probably doesn't matter. So I care about the thing that's running 100,000 times or 1,000,000 times or something like that, because that's where I'm going to get any gain. Okay? Real gain.
So how does it work in terms of enterprise applications? You have a lot of users hitting the site, but then still it's being executed in a particular browser.
Mm-hmm.
So it could memorize something that's happening in the browser, but then the user goes away, comes back to the same application, and he doesn't remember the previous.
Absolutely, all correct. All right, so the question, like in an enterprise, we have lots of different users hitting things. No, there's no shared memory, right?
Right.
But it doesn't matter because we don't actually, just like in an enterprise application, we may have 10,000 screens that we could view in the app. The odds that one user is going to hit all of them is pretty small. In fact, we build systems under the premise that no user probably will ever hit all of them, at least initially. So we care about the fact that they're going to hit a series of them. So I don't actually know that you and I have to have the same compiled code running in our browser, because if I'm going to a different set of features than you, we, by rights, should have a different set, right? Now there are things, and I don't know where this stands, there are some things they were actually doing for a while with V8 and with different things where on boot up it could sort of have memory about information. I don't know that that will ever, or if it ever makes sense to actually bring it to a browser level. But it was kind of interesting because there were people doing an experiment, which I thought was very neat, with V8 instances and with sort of more node-based stuff on servers, because they could basically snapshot the memory of where it was. And so instead of having something start up, boot up, and be in a virgin state, it could basically resume, like as in, this was my memory footprint, I'm up and running already. There was no resume time. It was an instant sort of on. Anyway, neat stuff in general, just an aside. Okay, does that all make sense so far? Yep.
So let's say we have a really large array, and instead of for loop, someone decides to use array map.
Yep.
Is the compiler smart enough to not create a copy of the whole array and just use the existing one and loop through it, or
Yep.
it depends?
Okay, it depends is the answer. So the question was about array map. And it's interesting because that is one of the things I didn't put on that list that people argue about all the time, okay? There are differences, and part of the reason is I didn't put these as maps because it is harder to reason about, because there is a closure created whenever you're using one of those functions. Now, that closure could be very simple, but if you think about the signature of map, map expects a function to call. So it's not like you can really just inline that as an expression. It really does expect a function in one case or another, okay? It can be highly optimized, but it expresses a function. The compiler, however, can be very, very smart about some of those functional methods in terms of immutability. In fact, if you look through the bytecode, you'll actually see times when it's talking about immutable versus immutable versus mutable sort of thesis, because it can be very smart about the sorts of optimization it applies in the case where something's truly immutable, like for instance, inside the middle of a reduce or a map if you're really pure in the function that you give. Now, not every one of those things is necessarily even in the current V8, but that's the cool thing about it, is they've made the groundwork for all those things to continue. But that's what makes functional stuff so interesting in general, is the fact that you're working always within, ideally, relatively pure, self-contained pieces, which is almost limitless in how you can optimize those. Right?
Do they publish the heuristics for like when turbofan kicks in?
Yeah, there's tons of stuff. If you, I didn't mention this earlier, but for anybody who's really feeling like they need a good day. Okay, well here's one great thing. If you want the x64 instructions, go see those. If you want to read the header files for either the bytecode or the interpreter, I also can send you those. But the real cool piece is this. If you want to read something that's actually is legitimately interesting about all this, this is the V8 blog. The V8 blog is fascinating because it's always talking about what's actually happening. In fact, look at the 95 right there, Mark, for you, the lighter V8. But the idea is that every one of them is tagged on the pieces that they're going through, and they actually are constantly publishing heuristics and constantly publishing how it works and what it goes. They're really open and they do a lot of great presentations, so you can also see them talk in a lot of places. This is where a lot of work's been done lately. There's a lot of cool things happening around WebAssembly in terms of what they do too. There's neat stuff.
We have 25 minutes.
All right, look at that. We're doing lovely.
You're not even, I mean, demo 99, I mean, Jesus, you're on 3.
The worst part was that we were going to write 6 through 98 together. Yeah. All right. Well, in the interest of making Mark happy. No, all right, so we don't want to do that. All right, so in terms of other sorts of things, and some of these are just going to be simple things we can talk through. And they're going to fall into a lot of the same categories, right? We talked about why we might use local versus global or avoid global or any of those things. We talked about don't use array methods. People say, you know, you should just use for loops. And just to be clear, right now, it is entirely true that using map does in fact cost you several microseconds. It's true. May not always, but it does today. It is irrefutable that it does cost you several microseconds. So somebody posting a very recent Medium article that I'm sure you can find by yourself who was completely outraged at the 10 extra microseconds over 1 million records that map took. And that does seem like something to be very upset about. So, yes, sir?
What's a microsecond?
It's a very tiny second.
Is
that a metric or old school?
It's
3 orders of magnitude.
3 orders of magnitude smaller than a millisecond.
Oh, okay.
Yeah, thank you. So just keep on dividing. It's mu.
It's a parsec.
But the gist of this is we're talking pretty small numbers when we're talking about the difference between them for most of these operations. And again, this isn't to say that if you really have a piece of code that needs to be optimized for whatever reason, and you need to do something, you're working with large data, and JavaScript doesn't happen very often, really large data, do what you need to do. I'm not saying that. I'm saying for your average case, the average programmer, we're wasting time doing these things, right? Everyone's probably heard of premature optimization. And premature optimization is the idea that we should not try to figure out how to optimize something until we know what actually needs to be optimized. I would actually say that in here, most everything we do is premature optimization for two reasons, and one that's really tricky. Number one, unless we're actually looking at the final compiled code with real data and real volume, we can't possibly know what's slow and what's fast. But additionally, how often does V8 rev? How often does Chrome change? It's constantly, like, little things are constantly getting faster. There's actually a really cool post about a cliff they specifically had in performance in React on V8 that they worked around recently. But there's really cool things in terms of what's going on. So we have to really be careful if we're going to choose to obfuscate any code for performance reasons here. You got to really have a good reason. All right, so going through these things, everything, just everything in that inlining section, all falls under the idea of you're smarter than the compiler, and here's the thing, you're not. Even if you went through and you know like 300 tricks to make things faster, he knows a couple more. And the thing is, it doesn't mean that there's not a place for handcrafted code to do these things. There certainly is. Okay, but it's the higher level, the abstractions. You know, one interaction with the DOM is going to be 300 times slower than probably half the JavaScript code in your system. So if we're spending our time here, we're wasting it. So all of these fall under, at least most of them in most cases, fall under the idea that if we're writing something and we call a function twice inside one loop with the same values, it didn't happen that way. It's going to work around that. It's going to optimize it out. This isn't an excuse to be sloppy, but it is a plea for writing things in a readable way rather than in a quote-unquote optimized way. Okay? So primitive operations versus function call, we already saw that that one doesn't really work out that way. Yeah, there's a tiny bit of overhead in some of what it does, but most of those things get inlined in that case anyway. Factors and simplify mathematical formulas, no, just don't. Cache objects to increase performance. I'm going to throw this one in here too. This is great. Does anybody know about how to use bit shifting instead of division?
Yeah.
All right. So, you know, if you're going to divide by 2, I mean, we have these relatively binary machines. We can just shift bits around left and right to multiply and divide by 2. Totally works. It's great. It's a fantastic way to go. That's a legitimate optimization tip somebody had on a blog. And in 2019, first of all, I hate to say this because it does make me just a little bit sad and feel old that I still know how to use this, but most people are going to look at my code and think I'm an idiot. They're not going to think it was brilliant. And second, if it was really an optimization, it'll do it for you. Just trust it. Today, does it actually divide by 2 versus that? No. But does it need to? Probably not. It's just we're not working in the same environment we were. For those of you who want to see what I'm talking about, that's what I mean. You can technically, even in JavaScript today, we can take the value of that and shift it by 2. And since we're shifting it, we're basically expressing division. Okay? Depending on how we go things. What's up? Oh.
You remember that average programmer you were talking about earlier? Oh, I'm so bad right now.
Do you want to derive the base 10 number system really quickly? I'll explain
What's that?
So okay, anyway, bit shifting, old school technique, but it is something that you see out there. Also, using excessive versions of bitwise and any sort of bitwise operators. I can't, and yes, sir.
So that's going to be optimized to something else or optimize itself or whatever.
Sure.
But I think, and I think somebody else asked about, like, maybe it's important to know, like, the rules of when it's going to do this optimizing. Because I write a lot of stuff that doesn't run 100,000 times, but I need it to be performant. And it sounds like if I want that to be performant, it's up to me. Because it's not being run 100,000 times, or 10,000 times, or in a user session more than 10 times sometimes.
Okay, so I want to clarify.
Okay.
I want to just make sure I break down this argument.
All right.
You have something that in a user session could happen as many as 10 times. And you think that you are writing code that is going to make that user's life better in one of those
It's
10
all
times.
I've got left to do.
I'm not criticizing. I just want to break down the argument for just a moment.
10 times in how often? An hour?
Yeah.
No, I guess I'm just saying, like at what point can I trust that the compiler is going to optimize it, and maybe I don't need to worry so much about every little detail, versus, well, the compiler's not going to optimize this.
All right.
And I do need to worry about it.
Thank you for demonstrating clearly the concept of premature optimization.
Yeah. It's what I do when I'm bored.
Okay, and you know what?
Taking it away from you, Mike.
You do you. If it is a therapy sort of thing, I say go for it. It's therapeutic. If it helps you work through things, I think you should optimize the hell out of it. All right? But I will say that perhaps, if you're unsure if it's going to be fast enough, maybe we wait and see. Possibly, we look and see if it's fast enough, and then if the compiler didn't do something sufficiently with it, then we go ahead and say, you know what, I'm going to spend a little time today. I'm going to go ahead and make that faster, as opposed to planning for it up front. It's me. It's
Well,
my
you
turn.
can always just write it the right way the first time with agreed upon patterns.
Oh, the right way.
Yeah, but what he just
We
said
don't
was
have to
every
argue
month
about
when
it.
they do an update, the right
Yeah,
way is the
but
wrong
I
way.
would never let my team write stuff 8 different ways just because shit, it doesn't matter, man.
Well, again, I think I have already clarified that the goal wasn't to say, like, look, I can just put one long plus sign. That wasn't the goal. But what I'm actually pleading for is that your team writes stuff in a way that's very readable, very legible, very understandable, and really good at talking to humans about, and going ahead and letting it figure out if those couple extra microseconds can be shaved off down here, as opposed to by making it harder to communicate by doing something like that. Just what I'm suggesting, possibly. Sir, please
Well-
rescue us.
Well, I'm gonna go the other way, and actually, I kind of get the same feeling. If you're coming from longer experience, the computers were not as quick as they are now, and maybe that kind of matters, and it's kind of stuck in our mind. And also, the
Call me old.
huh?
Yeah,
Well,
exactly what he said.
so anyway, experience. So anyway, so that's the thing. But when it comes to the other problem that people are trying to instill that in us a long time ago, was basically not to write code that's gonna be really horrible. And my question is this: understanding code is one thing. Let's put it aside.
No.
Well, listen.
Let's forget about your entire talk. For
Yeah, any argument that starts with we don't need it to be understandable, I'm out.
Whoa, hold on a second.
Alright.
Because basically what I'm saying, I'm taking your argument and flipping it upside down, literally 180 degrees. Can you actually write code that's gonna completely ruin the chances of optimization? Because that's really coming from
I
you.
gotta have the same question.
The
How do I
flip
choke
stuff.
the compiler?
Yeah.
So the question is, can you really, I mean, basically, can we be that dumb and basically get the compiler and not specifically to target the compiler and make something stupid. In a legit code where you're trying to solve a problem, okay, can you actually stumble on a solution that's gonna completely be like out of this world, that's like so stupid that the compiler is gonna say, no, I cannot really do anything about it?
Okay, so the question basically is, can we do it so stupidly that, in fact, can we make a piece of code so immovable that even the compiler can't move it? And the answer is yes, of course we can, right? We could figure out some way to say, I've decided to take my variables and instead of, this is me obfuscating now, right? I'm going to take my variable and instead of referencing them as variables, I'm going to store each letter in an array. And then I will reassemble the array by the numeric indexes of the digits of pi, and that's how I'm going to reconstruct my variable names, and hence I will be able to go and find if something is true or false. And I'm positive the compiler will have no idea how to optimize what I just talked about, because it's not possible to use a heuristic to figure out what I was trying to do. So it's possible, but I think the bigger question, and I'm not trying to avoid yours, the bigger question is it likely in an average case?
Okay, you missed me here on one
Okay.
thing, heuristics.
Mm-hmm.
So maybe I wasn't paying close attention enough. but really, you were talking about mechanics. All those examples that you gave,
Yep.
they appear to me like mechanical optimizations, okay? Which is easy for anyone, I guess, to understand. Heuristics, that's a little different. That's AI pretty much when it comes to code, which obviously comes from my question too, because the next question will be how machines can actually write code.
Sure.
But when it comes to that heuristics, so are you saying that the optimizations really prioritize on understanding the code?
The optimization is prioritized on the chunks of code that are used most, that are likely to have the biggest impact through a number of different things, including memory consumption, including execution time.
But based on
and
what?
use. Based on observing the execution of it, because it doesn't begin to optimize until you interact with the code. It's a just-in-time compiler.
But is it mechanical, or is this something that basically there is ingrained knowledge that, well, if it looks like a duck, we should figure that we're gonna use this methodology
Yes.
because we figured that in analyzing millions of lines of code, this is what you're trying to accomplish.
Yes, it's not one or the other, it's both.
Okay.
So there are route mechanical pieces that we can just do, right?
Okay.
We understand an abstract trajectory in one way, we can rewrite it in a simpler way. And there are other pieces that are much more like a heuristic, how it's being used, the inference of what's being called, how often something's being called, and the types and shapes of things it seems to be being called with that we make different decisions on. It's both. Okay? And it really is both. But one of the things that we didn't do yet, give me just 1 second, I'll get you. One of the things we didn't do, what we could play with, is that if we actually call a function with a number a bunch, and then we change it and we call it with a string, you'll actually see how it separates the code out and what it does. And that's purely based on the fact that it had assumed, based on the set of observations it had so far, that you're probably only ever going to do this. But that's not just mechanical. That's observation, right? And it's a decision based on observations to date that it revises if it gets new information.
Well, to me, heuristics is something that you got some intrinsic knowledge that you gained elsewhere versus observation, saying like tracking some statistical information that basically leads to mechanical branching. In essence, heuristics is I'm looking at this for loop and I can use a tree to represent it better. Okay.
Correct.
And yeah, if it's 1,000 nodes, well, maybe this is not a smart idea. But if it's 100, it's a good idea. So that's a heuristic to me. In terms of just tracking that, well, you know, the counter goes or whatever, that's not heuristic. That's just mechanics. So you're saying that heuristics plays a role, or
I'm
is it
saying they
basically
both play
just
a role.
smart mechanics?
I mean, a lot of it's smart mechanics, okay? But I'm saying heuristics does play a role.
Okay.
We're basically gathering information, and the team is continually working through this. So there's some aspects of that which are information gathering and someone making a decision. There's some of it which is more than that. But
Okay.
I assert that it's both.
So in essence, really the takeaway thus far is number one, make your code adhere to the good programming principles, and that's going to allow you guys to actually.
Your talk's over, Mike. Sorry, buddy.
So that's going to allow you guys to pretty much optimize the hell out of it and actually get the best performing code without having to worry about actually you having to deal with any.
I think the takeaway to that, and I agree, is, and I'll summarize this and then I'll grab for 1 quick second on this, is that I think that the thing that should still be, and we've all advocated this, but I think it's demonstrating more and more that your concern as a programmer should be expressing code in a way that's understandable, that's communicable to other people, and that we shouldn't be doing things intentionally to our code for the belief that somehow they're going to be faster, and especially based purely on belief, because it's a very much more complicated scenario these days than simply believing that the way I'm going to write it is going to have much impact in the way that it's actually going to come out the other side. So that would be my major piece.
So you have 5 at best.
All right, I will just take
10
questions and we'll be
minutes.
fine. It'll be all right. Go ahead.
It will
I
not.
was just going to address on the heuristic side. It is still a heuristic. Like you could look at that loop and say, oh, I can cache long array.length because it's an immutable. This loop is never changing the array itself. So you can have a heuristic that says if I'm looping over something, and it's never changed within that loop, the length of that array, I don't have to recalculate that length each time through the loop. I don't need to store it in a register. I don't need to do anything smart. That's still a heuristic. So a heuristic doesn't have to be AI. That's what I'm getting at. It's just rules. It's all just rules.
Everything is
It's all if
rules.
statements.
Yeah.
It's all just if statements.
But I think it's okay
It's
to have.
all binary, I get that.
But I think it's okay to have them where I separate it just a little bit, just to be clear, and we may not agree completely, but that's okay. I separated a little bit on the difference of things that I can analyze by looking at the code and things that I have to observe over the course of it, combined with knowledge I have about how things are used. I say that definitely gets in the role of
That
things.
the last part is what I was aiming at.
So.
The knowledge of how things can be used.
Right.
That's taken from outside of the code that it can be analyzed. So it's not mechanical. It's like saying, well, if you look at this duck, this is usually how it's best solved.
Right. And I would say a lot of it is very advanced mechanical per your definition, but I'm kind of in between in the sense that I think some of that borders on being heuristical. So we'll leave it there on that. So I'm not going to hit very much else because it doesn't much matter. The point is really the same. Let's hit these other ones really quickly. Things like this. There's a whole big piece about predictive stuff on putting conditions that are more likely to be true first. There's little things like this that we can maybe get small bits and values with. But things like we see with the with keyword, how half of Webpack uses a val. Bit shift operators are great if you're doing bit operations, and if you use them for something else, thou shalt be beat. And bit operations, while fantastic, and I'm happy I know them and can still convert hex things back and forth in my head, don't really have a need in most modern UIs. So for the most part, it's just the simple idea of let's write code that's pretty viable to communicate with. If there's really a good reason to go optimize it, do so, but we need to do it on empirical data. We need to do it on the idea of really seeing how something performs and knowing there's a really big problem, because it is, and I will assert, almost impossible at this point to look at a couple lines of JavaScript and actually know what the long-term performance of those are going to be, with the possible exception of me intentionally trying to do something, which I will leave open because I can, but with the exception of doing that, it's going to be really hard to actually know what that turns out to be. And that was the gist of this, right? The gist of this is that there's too much out there when one searches about performance optimization in JavaScript. We try to turn it into tips and tricks, but that's not it. It's not it in 2019. Your JavaScript is not what it was 10 years ago, 15 years ago, 20 years ago. It's a compiled language with a lot of work being done into it to produce a very tight language and very tight representation of something which is going to be very quick and optimized for the specific type of machine you're on. Because by the way, there are different optimizations if you're on ARM or if you're on an Intel box or whatever you're on. So we have different optimizations, and all of those things are happening for you. All your real job is to write reasonable code and, if need be, go back and optimize it. Still doesn't give you license to go write what I said. Don't store your variables in arrays indexed by pi. I think that's a bad idea. However, other than if you're trying to write an obfuscator, other than that, for the most part, that's my point.
One question.
Yep.
What is it? Webpack or the not Webpack, but the oh my goodness, the technology that allows you to run the bytecode straight in the browser.
Oh, you mean V8?
WebAssembly?
WebAssembly. There you
Yeah.
go. WebAssembly.
Oh, sure.
How is that really gonna be competing with the JavaScript
Flies
solution?
right into the same pipeline. And that's the really cool part. It's just not coming from up here, right? It's how we integrate in down here. We're further down in the pipeline when we do it. In fact, if you go look, and I'll leave it at this, if you are interested, you can kind of talk about, and one of the points on here is basically exactly how WebAssembly mixes into the engine. And there's a lot of articles about it because code caching for WebAssembly backends, that's exactly the idea. All you're really doing with WebAssembly at that point is you're expressing something at a lower layer that's more specific to how you want it optimized. And one can think about assembly as that, right? Assembly is a definitive guide, theoretically independent of some optimizations that might be placed on top that says, I intend to use it in this way. And it is mostly done, at least should be these days, when somebody has a very good and very clear assertion of why they want registers and what they want to keep around and that they don't want to base it on other rules, that they want to do it on their own opinion. But it's part of the pipeline. It's part of what comes in. And WebAssembly is really cool. I think WebAssembly is going to be the domain of certain things. I think it's going to be the domain of games. I think it'll be the domain of maybe some big data pieces. I don't see that we're going to be writing, despite a lot of people's opinions, and have been for 10 years now, that it's going to be the way that we do most front ends or we do most JavaScript. It's just not accessible in that way for most people. Some tools make it better, but that's my opinion. All right?
Multi-threading, that's one of the selling points for the WebAssembly, which is not possible under Java.
You can do worker threading. It's not that you can't do additional spawning of things, it's about shared memory, that's the difference. And I don't see that as being something that necessarily changes, at least in the JavaScript side. So, catch me afterwards, we can talk more. All right? Thank you very much again for the space.
No, thank you.
Thank you all for coming.